to talk about thermodynamics. So last time we got into, I think, Gibbs free energy. Which is delta G. And again, it is much like the name implies, is basically energy available to do some type of work. We actually can use Gibbs free energy to help us determine if a reaction is going to be spontaneous. So if the delta G is a negative value, then the reaction will be spontaneous. If the delta G is a positive value, then it will be non-spontaneous. We also saw, and we'll see a couple other ways as well to calculate delta G, but we talked about a couple up to this point. Delta G, just like delta H and delta S, can definitely be calculated by taking the delta G of your products minus the delta G of your reactant. So once again, you would go to the table, as we talked about, want to make sure that you look everything up to the correct state. And like normal coefficients in the equation, you want to make sure you multiply by the values you find in the table, and you can calculate delta G in that case. Another very common way we can calculate delta G is we can use delta G is equal to delta H minus T delta S. So again, that is our enthalpy. That is our entropy. And once again here, we do want to be careful of units, as we talked about. Enthalpy, again, is typically your kilojoules, and entropy is typically your joules. So we definitely, when you're using this equation, you do need to make sure that you, I guess, choose whichever way you want to go in terms of the units, but they do need to be in the same. We also talked about that you could use this equation here and sort of predict what type of temperature you would need for something being maybe a spontaneous reaction versus a non-spontaneous reaction, depending really on the signs that we see for delta H and delta S as well. We also saw at the end that we could use this to figure out if a reaction is spontaneous. We could also then use it to figure out at what temperature it would become spontaneous. Again, if it was obviously a non-spontaneous reaction. And we could do that by setting delta G equal to 0 and basically solving for the temperature, which would be delta H divided by delta S. So again, sort of rearranging that and solving for the temperature will give us really the minimum temperature at which it will sort of become a spontaneous reaction. And as we saw, I think the one we did was something like 835, I think, degrees Celsius to turn that reaction into a spontaneous reaction. Any questions on any of that stuff we talked about last time? So we talked a little bit about phase changes earlier on, and a reminder that when a phase change happens, as something again goes from, say, solid to liquid, liquid to gas, it does occur at the same temperature. And the two phases are in equilibrium with each other at that temperature. Remember that as you go from, say, solid to liquid or back, the energy required to do that transition is the delta H of fusion. And obviously it changes depending on the substance you're dealing with. As you go from liquid to gas or backwards, that is the delta H of vaporization, is typically the value that you would use for that. Those transitions occur at the normal freezing point, melting point for the solid to liquid sort of transition, and the normal boiling point for the substance at its transition as it goes from liquid to gas or backwards. Now, because these phase transitions are equilibrium processes, that means that delta G here will equal 0. And we could actually take this equation and solve for the delta S. And this would give us what is sometimes referred to in this case as we're going from liquid to gas. This was sometimes referred to as the entropy of vaporization, or the delta S of vaporization, basically. And in this case, because we are doing that transition of going from solid to from liquid to gas, we would use the delta H of vaporization value. And because this is water, we would use water's value, which is this guy right here. So that's the heat of vaporization for water in kilojoules per mole. This right here is 100 degrees Celsius, right? Which is the normal boiling point of water in this case. And if we do that, we do end up with 109 joules per Kelvin, or 109 joules as our delta S of vaporization. This does make sense in the transition of going from liquid to gas, because as we go from liquid to gas, we obviously are creating a lot more disorder, right? And we would expect that the delta S value here be a positive value, which it is. Now, if I was specifically going from, say, the opposite way, going from gas, say, back to liquid here, how would this calculation basically change? The only difference is this guy, right? If you go from gas to liquid, that is a exothermic process, right? Heat and energy is being given off, which means that would be negative 4079 divided by 373 will give us a negative 109 joules. And that would make sense as we go from gas back to liquid, as we're going obviously from more disorder to more order. And we would expect our delta S there to be a negative number. So again, depending really on sort of which way you're going, really the only thing that will change sort of the sign of delta H, which should correspond to the entropy change that you would see as you do this phase transition. First off, any questions on that there? By the way, this is the equation as we rearrange this guy. You get this formula here, delta S is equal to delta H over T. This is the one that should not be confused with the one we saw earlier, which is the delta S of the surroundings, which is this, minus delta H over T, yes? So once again, this guy has the negative. If you rearrange and solve for delta S of vaporization or fusion, whatever it may be, using G equals H minus T delta S, there is no negative there. Again, if you're solving directly for surroundings, obviously it does have the negative for like we were talking about earlier. So again, that's sometimes confused by people. They throw a negative where they shouldn't and stuff like that. Any questions on that there? Obviously, you could do a similar calculation and calculate something like the delta S of fusion. The only difference is obviously the delta H here would be our heat of fusion. And once again, that would be your normal kind of freezing point, melting point temperature for the substance. So let's take a look at one here. The enthalpy of vaporization for mercury is 58.5 kilojoules. And the normal boiling point is 630. What is the entropy of vaporization? So what is the delta S of vaporization for this guy? Would be our 58.5 divided by our 630 here, and going to give us something like 0.0929 kilojoules, or if we kind of convert it into joules, give us something like 92.9 joules in this case. We could probably safely assume we're going from liquid to gas in this case. Again, if they were talking about kind of going from gas back to liquid, they would probably specify something about condensation or something of that nature. Again, the only difference would be the negative sign, right? Any questions on that one there? So the next thing we're going to talk about is actually Gibbs free energy and our equilibrium constant, because it's been a while since we've seen K, so we don't want to miss out on it. So let's talk about a couple of other important sort of equations that involve free energy. This first one here is the delta G equals delta G naught plus RT natural log of Q. There's really two delta G's here. This guy here, again, is sort of delta G under standard state. sort of table conditions. So that would be your delta G of your products minus your delta G of your reactants if you had to calculate it from the table. You can kind of think of this guy on here. The first delta G is sort of delta G under non-standard conditions. So remember that standard conditions are basically sort of what you find in tables. And what that typically means is if we're talking about temperatures, 25 degrees Celsius, if we're talking about concentrations, everybody's 1 molar. If we're dealing with pressures, everybody is 1 atmosphere. So under sort of non-standard conditions, one or more of those things may not be the case. So maybe pressures aren't 1 atmosphere, molarity is not 1 molar, or maybe the temperature is not 25 degrees. The R here is our gas constant that involves energy. So it's the 8.314 version of it. Our T is our temperature in Kelvin. And our Q is our reaction quotient, which once again, as we've seen many times, is calculated the exact same way as we calculate K. So again, we take our products over our reactants. We also obviously use the coefficients as the exponents like normal to calculate that. So when we do reach equilibrium, a couple of things in the top equation sort of changes. Our delta G here becomes 0, and our Q will now become K, and it reduces down to this equation here that the delta G naught is equal to RT natural log of K. So obviously that's our equilibrium constant, and the R and the T are still the same as above, the gas constant and the temperature in Kelvin. So if you think about sort of delta G, there's a number of equations to sort of choose from. If we add, our delta G is our products minus our reactants. Also our delta G equals delta H minus T delta S. So there's a number of different sort of equations that involve delta G. As I mentioned earlier, definitely best to choose, kind of based on the information given to you. So once again, if you're just given an equation and nothing else, you need delta G, probably the products minus reactants to the table. If you're given H and S, or I guess you can calculate H and S, then the next one would be good. If you have something that involves the equilibrium constant, then obviously this guy on the bottom would be your choice. And then obviously if you have something that is under some non-standard type conditions, then obviously this guy up here would be your choice. So again, there's a number of different sort of equations involve free energy. Let's try one here. We also can look at this equation, this delta G equals minus RT natural log of K. And really the nice thing about this is it has the equilibrium constant in it, which means as long as you understand the equilibrium constant idea, which I hope at this point you understand, you pretty much can kind of figure out what's going to go on. So obviously, if we have a large value of K, as we know, we should mainly expect products to be there at equilibrium, which means we would expect probably the delta G to be negative and more spontaneous and allow the reaction to head towards the product side. If we had a small value of K, that means when we reach equilibrium, we should mainly have reactants, which means most likely delta G is going to be a positive value in that case, really favoring the reactants and not a non-spontaneous sort of situation. And lastly, if we have a K value that's equal to 1, then our delta G will equal to 0. And they're kind of both favored, if you will. A little bit of products, a little bit of reactants probably at that point. So again, the nice thing about that one, it does have the equilibrium constant. So you could just kind of think about it in terms of equilibrium constant and decide whether the reactants or the products would be favored. So while we try it, let's calculate the equilibrium constant here for the following reaction. Here's some delta G values from the table. G guy that had the equilibrium constant in it. That seems like probably a good choice here. So since our delta G naught here is really our products minus our reactants here, so we would go to the table, which is what these values are down here for. So the delta G naught in this case would be our products, which would be 3 times 0 minus our reactants, which would be 2 times 163.4 kilojoules. And that's going to get us 2 times 163.4. 326.8, and it is negative here, 326.8 kilojoules as our delta G. We also need to do our temperature here, so we'll add a 273 to that guy, gives us 298 Kelvin. I think that's all we need. So this is going to be minus 326.8. I'm going to multiply it by 1,000 to convert it to joules. The reason I'm doing that is because on the other side here, 8.314 joules per Kelvin per mole. Otherwise, I'm in some unit situation that's going to happen there. We're going to times that by a 298 and the natural log of K. I'm basically going to take everything on this side and bring it over to that side, right? So that will give me 326.8 times 1,000 divided by 8.314 and divided by 298. Going to give me 131.9 equals the natural log of K. Negative here and negative here turns it back into a positive, right, when we move over. That's also really important because the next thing we're going to do is take the inverse of the natural log. And if you have the wrong sign, you're going to get definitely the wrong answer here. So we're basically going to take E of both sides. When we do the E on this side, this just becomes the K. And if we end up with that over there, looks like 1.9 times 10 to the 57 would be our K value in this particular case. First off, any questions on any part of that calculation? Things also do agree. If we look at our delta G, it is a negative number, which would imply all right, so on this one as well, we do see a K. Remember, all Ks, no matter what the little subscript there is, they're all really the same thing. They're all equilibrium constants, which again means we will want to use the same equation that does have obviously our K involved. In this case, we pretty much got everything on this side, so we just need to kind of plug it in. So delta G naught would equal minus our 8.314, which is our gas constant. Once again, adding 273 to that guy gets us 298. The natural log here of RK 1.7 times 10 to the minus 6. That then gets us natural log 1.7 exponent button minus 6 times 298 and times 8.314. And that will get us 32914. These will be joules at this point. Remember that delta G is typically given in kilojoules. So if we divide it by 1,000, we're looking at something like 32.9 kilojoules in this case. First off, any question on that calculation? Once again, everybody agrees in terms of their signs. We end up here with a positive value of delta G, which means that reactants should be favored here. And that is definitely going to correspond to a low value there, right, for our delta, our K value. So everything does agree. So these are things, you might want to look at to make sure no calculation error was made along the way. Any questions on that there? All right, one last one here for the chapter. The delta G naught for the reaction is 2.6 kilojoules. In one experiment, the initial pressure of H2 was 4.26, I2 0.024, and HI 0.23. Calculate the delta G for this reaction and predict which way we would be going, reactants or products. Kind of one under standard conditions, one under non-standard conditions. Once again, if you're curious what makes this sort of non-standard conditions, it is the pressures that we see here. They are not 1 atmosphere each of them. So again, the sort of non-standard conditions. So we'll definitely use the equation that has both of those together, which should be, I believe, delta G equals delta G naught. And remember that it actually is a plus here, not a subtract, which is what a lot of people will do. RT natural log of Q. So in this case, we kind of have everything for us here. So our delta G will equal our delta G naught, which was 2.6. Once again here, I'm going to multiply it by 1,000 to put it into joules, really, because again, that is going to be in joules there, so we don't mess up any units. Plus our R, 8.314 joules per Kelvin per mole. Our temperature adding again 273 to that guy gets us 298. And natural log of Q. Q in this case, again, is products over reactants, which means it really, in this case, is the pressure squared of HI divided by the pressure of H2 times the pressure of I2. So we want to put those guys in, and that would get us up on top our HI, which is 0.23, and we want to square it. On the bottom there, we should have 4.26 and 0.024 in that case. Any questions on any of that there? Bless you. All right, so cleaning up, we'll do everybody on the right-hand side of the plus. So we're going to do 0.23. We're going to square it. We're going to divide it by 4.26 divided by 0.024. Do a little natural log action on it. Then times it by 298, times it by 8.314. And I believe that gets us kind of on this side, minus 1632.520879. So we're going to then take 2.6 times 1,000 and then add it to that answer. Going to yield us 967. These are in joules, are about 0.967 kilojoules if you turn it back into kilojoules in this case. First off, any question on the calculation there? That means the direction this guy should be heading is which way? That way, right? It is a positive value for delta G, which means reaction would favor the reactants and be sort of non-spontaneous. So we would actually head in that direction. Also, we see that playing with the pressures didn't really make it a spontaneous reaction in this case. Any questions on that there? So definitely these guys would be favored. Question on thermodynamics. I think that is it. Yeah. Delta S, delta G, delta H. Any questions on any of that stuff? Okay. That wraps up this chapter here, which is 16. Okay, so we're off to chapter 17, and we're going to talk about electrochemistry in this chapter, basically redox reactions and balancing redox reactions. The main part of the chapter is about galvanic cells, and we'll talk about galvanic cells, a little electrolysis towards the end, and a little bit about batteries in this case. So the beginning part here, we're going to kind of review redox reactions, how to balance redox reactions, oxidation numbers, oxidation states, just to make sure everybody's on the same page. So depending, I guess, who maybe you had for Chem 50, maybe you did some, maybe you did none, who knows? But at least everybody will be hopefully on the same page and be able to answer the questions that you need to answer. So let's talk about it. Electrochemical processes are what are referred to as oxidation reduction reactions. Those are usually just briefly sort of referred to as redox reactions. So redox reactions involve oxidation and reduction taking place. As you might remember from Chem 50, there's a whole sort of specific classification of reactions that fall under the redox big umbrella. So really, there's only kind of two big umbrellas of reactions: double displacement reactions and redox reactions. So redox reactions are reactions like synthesis or combination reactions, decomposition reactions, combustion reactions, single replacement type reactions. So those are all basically redox reactions. And really the purpose of redox reactions is the transfer of electrons in a lot of cases. So one of the three reasons why a reaction takes place is basically to transfer electrons, make a solid, and make water. So redox reactions really cover that sort of category of electrons being transferred. As electrons are sort of being transferred and moved around, energy can be used. Those electrons can be used to make some energy and do some work, as we come across here. When we talk about oxidation and reduction, we can look at something like this. And there's a couple of definitions of oxidation and reduction. Oxidation typically means that you lose electrons. Reduction usually means that you gain electrons. Some people remember Leo the lion goes grr. Loss of electrons, oxidation; gaining of electrons, reduction. Other people like the oil rig type of deal. Oxidizing is losing, reducing is gaining. So that's one way that you can remember it. There's also a few other definitions of oxidation and reduction that we'll see as well. And we typically come across those a lot of times in organic chemistry. It involves hydrogen and oxygen. So if something sort of gains oxygen, it's being oxidized. If it loses hydrogen, it's being oxidized. And if it loses oxygen, it's being reduced. And if it's gaining oxygen or gaining hydrogen, it's being reduced as well. So one very simple way to determine sort of what is happening, is something being oxidized or something being reduced, is just a simple number line. And on a simple number line, there's positive numbers to the right, negative numbers to the left of zero. I think that's how it used to work. And obviously, if you are losing electrons, will you become more positive or more negative? You will become more positive as you lose electrons because you have more protons. So if you look at the oxidation state or number and somebody is moving in sort of the positive direction on the number line from reactants to products, that guy is going through oxidation. When you gain electrons, you become more negative. So if you look at the oxidation state from the beginning to the end, and it becomes more negative, it is going through reduction. That's a super simple way to basically figure out what is being oxidized and what is being reduced. So for example, if we look at the oxidation states, which again are not necessarily always the charges that we assume are associated with things. Magnesium here in its standard state by itself has a 0 oxidation state. Oxygen also is naturally how it comes, has a 0 oxidation state. These guys do not get charges until they hook up on the right-hand side there. And on the right-hand side there, our magnesium ends up with a +2, and our oxygen ends up with a -2 sort of oxidation state. So if we look at, for example, the magnesium, is started at 0 and it ended at +2, which means it is becoming more positive and it is going through oxidation. We look at the oxygen, it started at 0 and ended at -2. It is becoming more negative and it went through reduction. We could actually take this reaction and split it up into its half reactions. And that's what we see here. The guy here is our magnesium going to magnesium with a +2, losing electrons. And that is what is known as the oxidation half reaction. And that is always how you identify the oxidation half reaction, because the electrons should always be on the product side, like they're being given off or released. Reduction, on the other hand, here, our oxygen is going to gain those electrons and make our guy with our -2 charge. And that is how you know it is a reduction half reaction. The electrons should always be on the reactant side. These two half reactions are called half reactions because if you add them back together, you get the overall reaction. And what should always happen before you add them together is you always need the same number of electrons in each half reaction. So however many electrons are lost by one should be how many electrons are gained by the other. And that may require, in some cases, the half reaction to be multiplied by a common number, or maybe both half reactions to be multiplied by numbers. But you always want to make sure before you add them back together that the number of electrons in each half reaction basically are the same. Pretty much anybody on opposite sides of the arrow could cancel or reduce. Electrons should always cancel out. And that leaves us on the left-hand side 2 magnesium plus an oxygen. These two ions will come together and make magnesium oxide in this particular case. Questions on that there? Now, in this case, it is 4 electrons because this is a balanced half reaction, and that's because there's 2 magnesiums, each lose 2 electrons for a grand total of 4. And there are 2 oxygens, which each gain 2 electrons each for a grand total of 4 that they are gaining. We look at another example here, our calcium and our oxygen coming together. Once again, calcium is 0 to start with by itself. Oxygen is 0 to start with. Calcium has a +2, oxygen has a -2. So once again, if you take a look, calcium starts at 0, ends at +2, becoming more positive. So it is the calcium here that is going through oxidation. Oxygen is starting at 0, ending at -2, which means it is the oxygen here that is going through reduction. Should that always be the case when we have a metal and a non-metal that comes together? It should always be the case because metals typically do what? They typically lose electrons, right? Become positively charged, and non-metals typically gain electrons. So whenever you're dealing with an ionic compound, which is a metal and a non-metal, that should always be the case. The metal should always be the one being oxidized, and the non-metal should always be the one being reduced in that situation. And again, we have our 2 half reactions that can combine to give us our overall reaction on the bottom. Now, there's also something that is referred to as the oxidizing agent and the reducing agent. The oxidizing agent is the substance that gets reduced, and the reducing agent is the substance that gets oxidized. They're called agents because that is pretty much what they do to the other substance. So in order for somebody to be reduced, they need to gain electrons. In order for them to gain electrons, they got to cause somebody else to lose electrons, which is why they're known as the oxidizing agent. In order for somebody to be oxidized, like we see here, they have to allow somebody else to gain those electrons, which causes that person to be reduced. So in our example here, the calcium which is being oxidized is the reducing agent, while our oxygen that is being reduced is the oxidizing agent. Both of those things, what is being oxidized, what is being reduced, the oxidizing agent and the reducing agent are always found on the reactant side. So always on the reactant side is where you find those guys. Any questions on that there? We go ahead and jump 1 slide ahead, apparently. And obviously in the previous example before that, the magnesium was being oxidized. So that's our reducing agent in that case as well. And our oxidizing agent would be our oxygen. Now, as I mentioned before, there are a couple of other definitions of oxidation and reduction. It is good to sort of note them. We probably won't see too many of it in here, but again, if you continue on to organic, you will definitely see it. So once again, oxidation means losing electrons. It also can mean that something gained oxygen from reactants to products, or something lost hydrogen from reactants to products. So those are three sort of definitions of something going through oxidation. Something going through reduction is basically the opposite. It can gain electrons. It can lose oxygen as it goes from reactants to products, and it can gain H2 as it goes from reactants to products. So for example, in this particular case, if we look, our tin goes from one side to the next, and it actually lost some oxygen, which means our tin here is going to be reduced. And by default, this guy would be oxidized, right? That's also the nice thing about redox reactions, which means if something is being oxidized, there has to be something being reduced. You can't have one without the other. So if you can pretty much identify one of them, the other guy is doing the opposite thing. We see carbon here, had no oxygen, but gained oxygen as we went to the other side, which again means the carbon is being oxidized. So in this case, our tin here would be our oxidizing agent. Our carbon would be our reducing agent in this case. In this particular case, you could have figured it out even without the oxygen and the hydrogen, because if we look just at the tin from one side to the next, this is -2, which means the tin here is +4. And the tin over here by itself is 0 in terms of its oxidation state. So once again, if you were just looking at the tin, started at +4, ended at 0, it's actually becoming more negative. And once again, that would tell you that it is being reduced in this case. So because there was a metal, you could kind of look at the oxidation states and stuff like that and still be able to determine it that way as well. Any questions on that there? So what really obviously helps us determine, what is being oxidized and what is being reduced is the oxidation state or oxidation number. So let's talk about, again, the rules to properly assign oxidation number or oxidation state. This is sometimes referred to as state as well. So the oxidation number is basically the charge the atom would have if all the electrons were completely transferred. So oxidation states and numbers sometimes confuse people because up until this point, they beat into your head pretty much the charges that you need for ionic compounds, like, bromine is -1, chlorine is -1, in these type of situations. And when you assign oxidation states for ionic compounds, they will still be those charges. So where we get some different sort of oxidation states is when we start talking about things that are actually covalently bonded, where they're sharing electrons, basically. So when things and elements start to share electrons, depending on who they're sharing with, the electronegativity of who they're sharing with, certain things can take on different oxidation states. For example, like chlorine could take on positive oxidation states rather than -1. Mn could have a lot of different oxidation states. You can see a lot of different states that are different than what you kind of have in your head for ionic compounds. So let's talk about the rules to apply oxidation numbers. The first one's pretty simple. Anything that's pretty much uncombined just by itself, naturally how it comes, will have an oxidation state of 0. So anything that's, again, pretty much naturally how it's found will be 0. If you have some type of ion that is given to you, a monoatomic ion, whatever the charge on the ion is also going to be its oxidation state. I would say oxygen is usually a pretty good place to start with. So when you're assigning oxidation states, if there is oxygen there, that's a really good place to start. Oxygen is typically -2, except when it actually is peroxide, then it will be -1. So in hydrogen peroxide here, the oxidation state of oxygen is -1, not -2. I would say probably 9 times out of 10, if you see oxygen, is going to be -2. How do you know it's peroxide? Usually there'll be an extra 2 on the guy next to it because it is actually O2 2-. So A lot of times there'll be that extra sort of 2 there as well. In addition, hydrogen is typically +1. The only time hydrogen would not be +1 is if it's in a sort of ionic compound with a metal and it comes second. Then it's like hydride, which is -1. Group 1 is +1. Group 2 metals are +2, and fluorine is -1. When you add up all your oxidation numbers, it needs to equal the overall charge on the molecule or the ion. So if it's a neutral molecule, then it needs to all add up to 0. If the ion is like a polyatomic ion, maybe it's got like a -2 charge, everybody needs to add up to -2 in terms of their oxidation states. So if we look at bicarbonate here, and we want to assign oxidation states for bicarbonate, since we do have oxygen, once again, that's usually a really good place to start with. Oxygen in this case would have an oxidation state of -2. And there are 3 of them, which gives you like a -6 kind of overall negative charge happening. Usually in a situation, if you have 3 elements like this, you kind of go right, you go left, and leave the guy in the middle for the end. So if we go to the other side, hydrogen is going to be +1. So we just got +1 for the hydrogen. We got -6 for all the oxygens. They all need to equal -1. That means in this particular case, carbon would have an oxidation state of +4 in this case. And that obviously would give us a -1 overall charge. The proper way to assign oxidation numbers would be for this guy, hydrogen would be +1, carbon would be +4, and oxygen would be -2, not the grand total of -6. So -2 is the proper one. The other proper thing to do is you should always include the charges, even if they're positive. So you should always include the charges, even if they are positive, when you're assigning oxidation numbers. Any questions on that there? All right, so why don't you try some here for each of these. Okay, let's take a look. We'll start here top. So oxygen here is going to have an oxidation state of -2. Lithium, which is group 1, will be +1. So really sort of an ionic compound. It will have really the same sort of charges we expect, +1 and -2. Going to our PF3, fluorine is going to be -1. There are 3 of them, which means to balance it out here, the phosphorus would have to be +3 in this case, since it does equal 0 overall. That means the phosphorus is +3 and our fluorine is -1 in terms of its oxidation state. Now, again, when you learn maybe ionic compounds, you think of phosphorus as having a -3 sort of charge, right? In this case, though, it's sharing electrons with fluorine, and fluorine is much more electronegative, right? Which means it's going to kind of pull the electrons towards the fluorine, making this phosphorus more and more positive. So in this arrangement, as it's sharing electrons, it takes on a more positive sort of charge than it would in, say, an ionic compound. In this case, on the bottom here, that's nitric acid, that's -2, that's -6. Going to the left-hand side, that's +1. In this case, it does need to equal 0 as there's no charge. That means in this case here, the nitrogen is going to be +5 in this case. And that would give us a hydrogen that has a +1 oxidation state, a nitrogen that is +5. And once again, the oxygen is -2, not -6. Any question on that one there? Coming down to dichromate over here, that's going to be a -2 for our oxygen. It gives us like a -14. This actually needs to equal -2 because of the charge. We actually have 2 chromiums here. That means each of the chromiums needs to be +6 in this case. +6 gives us a +12, -14, -2 overall. And in this case, chromium +6 and oxygen -2. Any questions on how to assign oxidation states? So really important to be able to assign oxidation states because it's going to help you obviously balance things, figure out what's going on with what's being oxidized and what is being reduced. Any questions on that there? Okay, next thing we're going to talk about is how to balance redox reactions. And obviously, if you have a simple redox reaction, as we talked about earlier, basically all you have to do is make sure you have the same number of electrons on both sides of, or in both half reactions before you add them together. When we balance redox reactions in either acidic or basic conditions, it's done a little bit different, the steps that we take to balance them. And we're going to go through it again just to make sure everybody here is on the same page and knows how to do these. So let's say we wanted to balance this solution here in acidic conditions to start with. So there's several steps that we take to help us balance this out. The first step is it's usually a pretty good idea to sort of figure out what is going on, who's being oxidized, who's being reduced. So if we look at the iron, for example, its oxidation state is +2. We just did this guy in the previous example. That is +6 and -2. The iron here would be +3, and the chromium here would be +3 as well. So the first thing that we really would want to do is split up this reaction into the two half reactions. And the way that you do that is pretty simple. You take the elements that are the same on both sides, opposite sides, and put them together. So obviously we have an iron on the left, goes with our iron on the right. We also have a chromate, our chromium on the left, goes with our chromium on the right. So the first thing we want to do is kind of split up the half reactions. We also want to kind of figure out what is going on. So if we do our little number line and we look at iron, iron is starting at +2, which is like here, and it's ending at +3, which is going in this way, becoming more positive. So in this case, the iron here is going through oxidation. By default, that means the chromium here is going through reduction. And we could verify that by going chromium is starting at +6, which would be over here, and it's ending at +3, which would be moving in this direction, the negative direction, which means it is going through reduction. That means that my reducing agent would be which one? It would be this guy would be my reducing agent, and it is the chromium here that would be my oxidizing agent. So it's really good sometimes to figure that out at the beginning because it could help you make sure that you didn't screw up as you go through. So this is really our oxidation half reaction, and that is our reduction half reaction that's going on. So once you split up the overall equation into the two half reactions, the next thing you do is you balance all the elements other than oxygen and hydrogen, just like a normal equation. So we have one iron in each on both sides on the top, but we have two chromiums here and only one here. So we would put a 2 in front of the Cr3+ and balance it like normal. Once you've balanced everybody other than oxygen and hydrogen, it is time to balance the oxygen. And the way that we balance the oxygen in this method is what is known as adding water. So we add water to whatever side needs the oxygen. So we add that to whatever side needs the oxygen. The problem though with adding water is we're not just adding oxygen, but we're also adding hydrogen. So for every water that you add to one side, to the other side, you need to add 2 H+ to balance out the hydrogens. So how that works is in the top reaction here, there is no oxygen, so we don't have to worry about it. In the bottom one, there's 7 oxygens, which means on the right-hand side, it needs the oxygen. So we're going to add 7 waters. That is going to balance out the oxygen. But because we added 7 waters, we will need to add 7 times 2, which is 14 hydrogens to the left-hand side. Any questions on that? By the way, if you're balancing a redox reaction and you have an unequal number of hydrogens to start with, you could add H plus to the other side to balance it out. Somewhere along the way, you need to do that to make sure that you end up. At this point, we've now balanced all the elements. We balance oxygen, hydrogens. The next thing that we're going to do is actually balance the overall charge on each side. And to balance the overall charge on each side, what we are looking to do is we're going to add electrons next. And we want to add electrons to whichever side needs the negative number. The goal is to get each side of the arrow to the same charge. It doesn't have to equal 0, but it needs to be the exact same charge on both sides. So if we look at the iron, on the left, we have a +2. On the right, we have a +3, which means we need to add 1 electron to the right-hand side, and that would give us a -1 for a grand total of +2 on the right and +2 on the left. On the bottom here, this is basically +14. This is basically -2. No need to go individual there. The overall charge adds it up for you. Why do the extra work? That is a +12 overall charge. This guy gives us a +6, and this guy gives us 0. That means the negative electrons in this case will need to go to the left-hand side. And to balance out the charge, we would need 6 electrons there to do that. And that now gives us -6 for a grand total of +6 and +6 on both sides. Any questions on that there? The good point of figuring out what is being oxidized and what is being reduced is at this point, you can figure out, did you screw up? You know that this is the oxidation half reaction, which means my electrons should be on the product side, which they are, so that's good. This is the reduction half reaction, which means my electrons should be on the reactant side, which they are as well. You should never, ever, ever, ever add electrons to the same side. Yes, they should always be on opposite sides of the arrow. Any questions on any of that there? All right, so gonna kind of recopy this, I think, just to clean it up. So we have on one side Fe2 plus goes to Fe3 plus an electron. On the other one there, I believe we had 6 electrons, if I'm not mistaken. 6 electrons, 14 H pluses. Pluses plus a little dichromate and 2 to Cr3 plus, I believe. I got that right there. Right? All right, at this point, once we've added the electrons, we also have 7 waters there. I think we're good. We're ready to really add these reactions back together. And when you do add those electrons, as I mentioned before, it really is sort of easiest to look at overall charges on both sides. Some people like to go individual elements, and that's kind of silly. Just look at the overall charges. We need to make sure that we have the same number of electrons in both half reactions. In this case, we actually don't. We have 1 electron there and 6 there. So that's going to require us to take the top reaction and multiply it by 6 so that we end up with the correct number of electrons. I'm going to write that underneath, and that's going to give me 6 Fe2 pluses, 6 Fe3 pluses, plus 6 electrons. Now that I have the same number of electrons in each side, in each half reaction, I'm ready to add these guys back together. Remember that anything that is on opposite sides of the arrow that is the same can be reduced down or cancel out completely. The one thing that should always cancel out completely is the electrons. So the electrons should always completely cancel out, which it does in this case. And I don't believe there's anything else to cancel. At this point, everybody on the left-hand side of the arrows and both stay on the left, and everybody on the right-hand side stays on the right-hand side. This gives me 14 H pluses plus a Cr2O72 minus plus 6 of the iron 2. Gives me 2 of the Cr3 plus 7 waters and 6 of the iron 3s here. And if I did everything correct here, this should be the balanced redox reaction in acidic conditions. Now, how do you know if it's balanced? It actually needs to be balanced basically in 2 ways. It needs to be balanced like a normal equation, which means you have the same number of elements on both sides. And it also has to be balanced that you have the same overall charge on both sides. Again, does that equal 0 on both sides, but it needs to be the same number. So if we quickly look at it there on the left-hand side, I got 14 hydrogens. Right-hand side, 7 times 2 is 14 for the hydrogens. 2 CRs on the left, 2 on the right. 7 oxygens on the left, 7 on the right, and 6 irons on the left and 6 on the right, which is good. Overall charge happening here, that is a plus 14 from that guy. That's a minus 2, and that is a plus 12, which is a lot of math at this moment, but I believe that is a plus 24. If I did the math right, I hope, or not, I don't know, somewhere in that ballpark. This is a plus 6 for that guy. That is a 0, and that is a plus 18. And that also should be a plus 24 overall. And we would be balanced in this case, both ways. And we put a box on it. Yeah. Any questions on that there? This is balanced in acidic conditions. And the reason I know it's balanced in acidic conditions is, what do I see there? H plus. Yeah, so I see H plus tells me it is balanced in acidic conditions. Now, you also sometimes need to balance these guys in basic conditions. And there are a couple ways you could do it, but frankly, the simplest way to do it is to basically just balance it in acidic conditions and then kind of turn it into basic at the end. So what we're going to do is, I'm just going to rewrite it here, the equation. So if you need to balance something in basic conditions, you just balance it in acidic conditions, just like we did there. And at the end, you could turn it into basic by doing a simple little procedure. And that is, we will then add to go to basic, we're going to add OH minus to both sides. We're going to add OH minus to both sides. And the amount of OH minus that we add will equal the H plus. So the amount of H plus that's there is how many OH minuses we should add. So in this particular case, we have 14 H pluses. That means on the left-hand side, we will add 14 OH minuses. And on the right-hand side, we will add 14 OH minuses. On the side where there is OH minus and H plus, OH minus and H plus make water. Yeah, so they will come together to make 14 waters. And typically what will happen at this point is you'll usually have some waters on the other side that you could either cancel or reduce down. And in this case, we have 7 waters on the right, which we could subtract from the 14 on the left. And that will leave us a net of 7 waters on the left-hand side, plus our Cr2O72 minus, plus our 6 iron, gives us our 2 Cr3 plus our 6 iron 3, and our 14 OH minus. And if we didn't screw up anything, this would now be balanced in basic conditions. It should still be exactly the same way in terms of elements on each side. So 7 times 2 is 14 hydrogens, 14 on the right. 7 oxygens on the first guy, 7 in the second is 14. 14 oxygens on the right-hand side, 2 chromiums on the right and left, and 6 irons on the right and left. Overall charge, this guy contributes 0, this guy contributes -2, this guy contributes +12, and that is a grand total of +10 on the left-hand side. Right-hand side, that is a contributing +6, that is a +18, and that is a -14. That gives us a net +4, and 6 is +10 on that side. So it is balanced again, both in charge on both sides and elements on both sides. And again, I know that this is balanced in basic conditions because I see there hydroxide. Yeah. So if you see hydroxide at the end there, it's definitely balanced in basic conditions. As you see above there, it is balanced in acidic conditions. Any questions on any of those steps? Did you guys do this in 50? No, not at all. Ish. Okay, we'll do a couple more next time to make sure everybody's on the same page. So I said sometimes people do